called tripod. Thank you. Thank you, Gregory, for the introduction. I will be short because I calibrated myself to 30 minutes, including questions. So I will be very short. We will conclude very soon. Don't worry. So the title of my talk is Managing the Cloud to Edge Continuum Under Uncertainty via AI with Performance Guarantees. I think a lot of what I will be saying echoes what Jose Camacho just said. So I think there will be some bridges, maybe. First of all, uncertainty. So you mentioned a lot uncertainty in data, and uncertainty is what we have in real networks. And if we are not sure about our data that we use to train the model, etc., and of course, always we cannot be sure. I mean, we are always not sure. Then analytical results can help us, right? Because we can say whatever the data we have, the theorem says we will converge to the optimum. The theorem says our we are suboptimal, but the gap between the optimal solution and our solution is bounded. So I think like some mathematics can help faced with the uncertainty of our data. Now this thing always works. No. Okay, it was working and now it is not. Okay, I will use my finger that always works. Okay, yes. Ah, no, I know why it was not working. Okay, now I think it will work. So this is the setting of which I will talk today. I will talk about a network which spans from the cloud to the edge. So at the edge, we find Wi-Fi access points or base stations. And if we go upward, we go to the central data centers of an operator. And then on the one hand, we have users who have smart devices like smartphones, smart glasses, smart cars, or smart whatever you want. And these users want to consume some applications from some third-party service providers. For instance, Netflix, or in the future, we may use metaverse. I hope we will never be trapped into the metaverse, but anyways, or online gaming, or augmented reality, etc., etc. And so the setting of my talk is the one in which the network operator virtualizes its infrastructure and allows these third-party service providers to deploy part of their applications into the network up to very close to the users. So in this context, there are many problems that I studied and in which I applied some AI techniques. The first problem is placement. So if each of these service providers have different components that represent their applications, where do we place these components across the network? Second problem is resource allocation. So if in each node, the network operator has some memory, CPU, storage, how can it allocate properly the right amount to each of these third-party service providers? And then other problems are routing of user requests and pricing. Today, I will focus on just two problems: placement and resource allocation. But we also can discuss about the other if during questions. Before talking about these two specific problems, I will give a general comment. As I said at the beginning, networks are full of uncertainty. So they are an uncertain environment. The first source of uncertainty is the users themselves, because yes, they are predictable in some way, but the actual load of requests is not known in advance. So there is uncertainty about that. There is also uncertainty about the costs of our decisions, where cost can be energy cost or monetary cost or quality of service cost. So we are full of uncertainty. So if there were no uncertainty, we could use some deterministic optimization problems to take all these decisions, mathematical programming, etc. And this is what a lot of papers 2 decades ago maybe were focused on. But the interesting setting is the one in which we acknowledge uncertainty and we try to cope with it. We have, I think, 2 types of uncertainty. One that is when we know at least the probability distributions behind these uncertain events. We know at least the probability distribution of user requests, etc., etc. If we know these statistical characterizations, we can apply some stochastic or robust optimization. But if we know nothing, this is when artificial intelligence can be useful. And this is more or less the setting on which I will talk about the 2 works. So the first one is called, is about what we call inference delivery networks. And the main contributors are Taleb Salem, Gabriele Castellano, and Andrea. So I am not the main contributor, I want to emphasize that. But still, I want to talk to you about this. So we know that when we have to perform a supervised learning task, like classifying images, we can use many models, many different models, with different levels of complexities. And usually, if you want high accuracy, you need largest models. So you need to consume more memory, more CPU, etc. And there are techniques such as the distillation technique, in which you can take a big model, very precise, and you can, let's say, convert it in smaller versions of these models. So this is what exists in the machine learning community. And we start from these observations to propose the following question. So if we want to deploy these models in the cloud-to-edge continuum, so how do we decide where to place these models and which versions of these models it is optimal to place in each of the network nodes? This is the question we formulate. And let's say the system, we call the system in which we deploy these machine learning models across the network inference delivery networks, because instead of content delivery networks that maybe most of you are familiar with, in content delivery networks like Netflix or Akamai, etc., we want to spread content, but in this case, instead, we want to spread models to perform inference. Please interrupt me if you have any question. So again, if we come back to this picture, and let's assume that we have 3 machine learning applications performing 3 different tasks. For instance, the first application is a conversational agent. A second one is an augmented reality. A third one is another augmented reality application. And basically, the device of the user asks for an inference, like sends an image and tells, give me what is if this image is a cat or a dog. And so to have the answer, we want to deploy these models across the network. So first of all, we assume that we have already trained these models somewhere. And now we have trained models of different size, and we deploy them in the network. There is a trade-off here, because if we want very fast answers to these inference requests, we need to place the models very close to the users, like in the base station, for instance. But there, the capacity is limited, so we can just deploy small versions of these models. So the precision is a bit less. While if we want to have very precise models, then we have to tolerate more delay. So there is this trade-off that must be solved. And this must be solved for many concurrent applications that are deployed on the same physical network. So this is the setting we want to solve. And so now I will give just a few details about that. So let's assume let's focus on one task, like augmented reality, and users send a sequence of requests, and there is a repository of this application where a big model is always deployed, and that can answer any inference requests. And there is a path from the users to this repository. So what we can do is that along this path, we can deploy some models. And then we can choose for each user request, which of the models we want to answer that inference request. To each model, we can associate a cost. This cost accounts for the round trip time, the elaboration time, and also the inaccuracy. So this is where the compromise arises. And of course, every time we try to select the best model to answer the users. We have at each time slot a sequence of requests for different tasks, okay, and from different input nodes, so from different users. And our decision is a placement decision. So where do we place models, and at which versions of the model, actually. So for every time we fix a placement decision X, well, it doesn't work, okay, just X, and we observe some sequence of requests, we pay a certain costs across this time slot. And we can compare this cost with the default cost, that is the one that we would suffer if we didn't deploy any model across the network. Just we would use the model that is in the central repository. And the difference between the two, we call it instantaneous gain. Now, what we want to do is we want to maximize the gain, of course. So at each time slot, we want to take placement decisions so as to maximize the gain. And instead of measuring the gain directly, we measure the regrets. So what is the regret? Before defining the regret, let's focus on this X star. X star is the placement decision that an omniscient decision maker could make, like God, who knows already what are the exact sequence of requests from now to the end of the experiment. God can compute that perfect placement. Okay, this is an ideal, of course, an ideal solution that we can achieve in reality. But we can compare our sequence of decisions with this ideal best decision. And the difference of gains we have in the two cases is called regret. In order to have some performance evaluation that is very conservative, the regret is computed under adversarial setting. So this difference of gains is computed in the worst case, assuming that the sequence of requests come in the worst case, in the worst way possible, assuming that users ask requests just to hurt our system. Okay? This is a pessimistic assumption. Of course, in reality, that is not the case. Users just send requests doing their life. But if our system behaves well in this worst case, then we can be sure that our system behaves well also in normal cases. And okay, we propose a simple algorithm. Here I show it in a simplified way, but it's practically a subgradient ascent algorithm. What I want just to communicate to you is the type of results we can have. So we can show analytically that the regret that I just defined before grows sublinearly, meaning that the average regret per time slot goes to zero, meaning that we approach the ideal solution of the omniscient decision maker, even if we know nothing about the sequence of requests at the beginning. So this is, let's say, oblivious with respect to data. So even if data are very bad or whatever you want, we can show that we approach the optimal solution. And some numerical results confirm this finding. And so we compare our approach with some ideal baseline. And we compare this solution both in terms of latency and inaccuracy. And in effect, we approach also in practical experiments the ideal optimal solution. Okay. So this concludes the first part of my talk, in which I talked about placement. Now we'll switch to resource allocation. I don't know if it's worth maybe asking questions now regarding the first part, or if anyone has questions. Otherwise, I can continue. Okay. So the second paper I will talk about is cache allocation in multi-tenant edge computing, an online model-based reinforcement learning approach. So this is basically the work of Ayub Ben-Amer, who is here and who got his PhD at the end of 2023, and Tijani Shed, who is professor at Télécom Sud Paris. So this time we focus on one node only, an edge node, for instance, a wireless access point, in which the network operator has some resource, for instance, storage. And service providers in this case are content providers like Netflix, YouTube, video streaming, if you want. And the network operator can partition this storage and allocate slices of this storage to these third-party service providers, who can place into the allocated slice the content they want. So now, when users requests video segments, the edge node can directly provide the video segment if it is present in the cache. Otherwise, for all the segments that are not in the cache, they have to be retrieved from the repository of service providers, generating upstream traffic. And this upstream traffic that we want to minimize, because operators pay to generate it. And to do so, we think about a simple control loop in which we monitor just the volume of upstream traffic. And continuously, with the reinforcement learning agent, we change the allocation, and we aim to decrease the upstream traffic as much as we can. So we model the problem as a Markov decision process in which the state is the vector of allocated cache slots to each service providers. That we define nominal cost, which is basically the volume of upstream traffic. This is stochastic. This is a random variable, because even if we fix the allocation, requests from users change randomly, and so the upstream traffic changes as a consequence. Actions that we take are modifications of the allocation. And every time we take an action, we produce some spurious, let's say, traffic. We call this traffic perturbation traffic. For instance, if you give more slots to the yellow service provider, we need to fill these cache slots with some content. And so we need to generate this traffic just as a consequence of our actions. So actions do not come for free, but they have a cost. So the total cost is the sum of the nominal cost generated by the users and the perturbation cost generated by us just to change our decisions. And the goal is to minimize the cumulative cost. So this is the usual setting. Now, we can use deep learning, of course. And actually now, like in the last year, every time I send a paper, the reviewer always asks, why don't you use deep learning? Because it's state of the art. Why don't you compare with deep learning? Because deep learning is state of the art. So let me tell you why I cannot use deep learning. First of all is that we want our algorithm to work online. So we cannot afford long training steps that are required in deep learning. We want this algorithm to start from scratch, to run in the network, a real network that is up and running, and we need to take good decisions immediately. So if we use deep learning, we would spend tens or hundreds of years to collect enough information in a real network just to have a good Q table at the end, a Q function at the end. And of course, no network operator can accept to run their network in a bad condition just to train an algorithm, right? So, I mean, deep learning is nice in papers, but in real systems, most of the time we cannot use it. Another barrier is that a system has some time scale that limits the number of actions we can take. So for instance, we are assuming that we can change our cache allocation 4 times a second. So in order to collect enough data for training a deep learning agent, we will need hundreds of years with this slow pace. I mean, real systems are slow. So we have to find sample efficient methods to manage them. Moreover, deep learning does not provide any analytic guarantees, and this is instead what we want. So this is why we use the old dear QLearning, but with a small but important modification, because we use it in a model-based setting. We exploit in particular the structure of our cost. So our cost is composed of 2 terms. One that is deterministic and is that it comes from our modifications of the allocations, and we know it perfectly. What we don't know is the nominal cost. It's the upstream traffic generated by users. This part is the only one that we need to learn. So our idea is to train a supervised learning model, a simple one. We use polynomial regression to learn this unknown function. And then we apply QLearning not on the real cost, but on the simulated cost coming from this supervised learning model. This has multiple advantages. First of all, we can simulate many transitions, like theoretically infinite transitions, instead of just making, even if in reality we just make 4 transitions in the physical system. In the with this simulated approach, during the functioning of the real system, we can instead simulate 200 transitions. So we use the few collected observations just to train the model of the nominal cost, but the Q table, we learn it on the modeled and simulated cost. And so as a consequence, we can learn a good Q table very fast. And results compare this. So you see here that our approach is the black solid line. And after 40 minutes, we go to a decision that is close to the optimal one in terms of total cost. Also here we compare model-based reinforcement learning with model-free reinforcement learning, in which we adjust the Q table just based on the 4 observations I said we collect on the real system. And we see that this is the optimal allocation. We converge to it very fast, and we are stable. While here, we need a lot of exploration. And the analytical results that we find is that the allocations that we take over the time slots converge with probability 1 at the point that is boundedly close to the optimal allocation. Okay, and we don't move from that pseudo-optimal allocation with probability 1. So once we arrive there, we don't move except some rare case which vanish to 0. Yes?
How big of an applicability that the supervised model is a biased estimator?
Yeah, that is a big hypothesis. So if you want an unbiased estimator of the nominal cost, is just the average of the observations. This is an unbiased estimate. So you can use that and you respect the theorem. But if you use, we don't use that because it would be very inefficient. We use instead the polynomial regression, which is not unbiased. So in practice it works, but we don't respect this theorem. So yeah, so this is what so theory is nice. It can give you guarantees, but most of the time under assumptions that are difficult to meet. I mean, we can meet these assumptions, but then practically we would observe a less fast convergence, even if then we can know that in theory we converge. So there is also a trade-off between, if you want to boost things, you may violate some of the assumptions, so you don't have the support of the theorem.
So condition means sufficient, not necessary. With your other estimator,
Yes, that's true. It's sufficient but not necessary. Then, okay, we look at this picture, we say, yeah, we converge, that's true. But we cannot be sure that after a while, maybe we don't converge anymore. I mean, we don't have the analytical strong proof anymore. Yes.
If I can make a comment.
Yes, please.
The comment you made before, I think there is always, well, it's well known the trade-off between bias and variance.
Yes.
So with infinitum data, you can guarantee that you are reducing the variance, but not necessarily the bias. So if you use a model or data that is poor quality, you don't improve. So you get a biased model and there's error that is maintained even in the future. I don't think here is you are showing with results that is working. Theory, as you say, is good, but bias is all over the place in real practice.
Yeah, well, then a simple average for sure doesn't have any bias. So when I say bias, I mean that the empirical average converges.
There is no bias with averages if your model is static. Is not moving.
If the traffic is static, stationary.
Yeah, it's stationary. That's the word.
Yes.
Yes.
If it's not stationary, then you need infinite amount of observations in a limited time before the trust changes, and it's visible.
In the end, it's still working, so that's fine.
Yeah. So again, theory is nice, but if we look very closely to the assumptions, we have to be careful that many times these assumptions are not, are difficult to meet. But still, when we derive an algorithm, it's better to have some theoretical characterization than having completely nothing. That is what we usually have with deep learning. Yeah, other questions, other observations? If not, let me conclude. So AI is an effective tool, it is an effective method to manage systems with stochastic and unknown behavior. It provides good practical performance and also analytical guarantees if you choose the right artificial intelligence methods. In all my work, I tested these things in a simulated environment. So this is a limitation. So if now I take this and I put it on a real network, I guess many complications arise that I didn't observe. So this is a big to-do. And the concern that I would like to share with you and have your opinion is that about this deep learning, that is always there. And I think it's an opportunity for us because we can do a lot of things with that. But it is becoming also a barrier. If you have a good idea that is simple, that works, you might be blocked, not published, and attacked because you didn't compare with deep learning. And we know deep learning is hard to make it work, doesn't provide any theoretical guarantee. So if every time we impose researchers, so if reviewers impose researchers to go through the pain and the waste of time of deep learning just to make an idea accessible to the others, deep learning may become a barrier. This is my opinion. I don't know if you share my vision. Yeah, but then they would say, yeah, but you didn't find. What I also had is that, yeah, but you are better because you didn't choose the right hyperparameters of the deep learning model with which you compare. And this is an infinite race because since deep learning doesn't have any theoretical guarantees, you can only do trial and error. And if you say this is the best deep learning model I have, the others could always say, yeah, but it's your fault. You didn't manage to tune it well. So, yeah. I concluded, so thank you. Yes.
It's just a remark regarding the statement about deep learning. So I didn't face that issue yet, but if I would understand you.
Yeah.
But I would say maybe in your work you should defend that running deep learning requires dedicating hardware, which is not always feasible in the setup that you consider. And also you could say that deep learning is not good for environment. And that, but it's a problem. I listen to people that are laughing, but it's not a problem. And actually, generative AI and AI in general is a problem. And saying I want to use AI everywhere is a bad idea. And this is what has been said in the previous talk as well. Because most of the time you cannot interpret what is there, so you don't have guarantees, as you said, and also you have a dramatic environmental cost. So
Yes.
and I think this is good arguments that you are not counter.
Good point. Good point. Yes, I will break it down.
Any other questions or remarks or comments? I think we can conclude now then. Thank you very much.
Thank you.